Greetings. In this series, we are going to look at mathematics from around the world. Math is a subject that is studied around the world by various peoples and has involvement in culture at various levels. We have images used as artwork from geometry, and we have geometries that were studied because someone was looking for one thing, discovered another, and then that was applied to something else. In this series, we want to look at mathematics from around the world and the various things that connect us as a people in a beautiful creation. I hope you enjoy worldwide mathematics. In this video, I'm going to prove the Pythagorean Theorem. And before you think, well, this isn't exciting, I want you to think about the fact that the Pythagorean Theorem is probably one of the top most proved theorems. There are so many people that have made proofs for the Pythagorean Theorem. Another similar thing that is often proved is the proof for the harmonic series diverging. When I took an analysis course when I was working on my master's degree, we discussed that, and we got extra credit if we could find a large number of these proofs, and then it ended up we had to be able to do one of these proofs on one of the tests. Today I want to introduce the proof of the Pythagorean Theorem by the U.S. President James Garfield. He provided this proof in 1876. Before we begin with this proof, we need two other theorems here to help us along, and these theorems are probably familiar to you because you've seen them at some point in school, most likely. And so we're going to use these two theorems to help us along, and we're going to prove the Pythagorean theorem that given a right triangle in the plane, a squared plus b squared equals c squared. And I'm starting out with my triangle in this position. I'm doing this not because it has to be in this position, but because I want to illustrate something that you may not have been told, but I think it is helpful for us as students to be told this because it helps us organize ourselves. A, B, and C are arbitrary variables. They could be anything. It's commonly taught, though, that this is A, B, and C for these side lengths. If you put your triangle in this position, though, the A, B, and the C can be made a little more solid, I think, in our thinking, because with the A on this side, the B down here, and the C here, this A is the altitude of my triangle. Altitude begins with A. This B side is the base of my triangle. B is the beginning of base. Now, we can't quite do something with C, but if we have A and B established firmly, then C has to be the hypotenuse. One of the things that I see students mix up when they try to use the Pythagorean theorem is that they try to make this hypotenuse something other than C, and so when they're trying to solve for things, they get wrong answers because of this bad understanding of what the A, the B, and the C stand for. They're not interchangeable. A and B can be interchangeable because you're adding those terms, but C has to be the hypotenuse. So if we think about the A being the altitude of the triangle, the B being the base of the triangle, then that leaves that C has to be the hypotenuse. And that's going to help us with labeling as we try to do problem solving with the Pythagorean theorem. That's not really the focus here today, but I like to start in this place. Now, what Garfield does is he takes his given triangle in the plane and he's going to create a geometric transformation. He's going to move it somewhere else in the plane while maintaining the original. So this is our pre-image, and we're going to create an image of this triangle somewhere else in the plane. And where we're going to do that is we are going to create the triangle out here. All right, we've created a copy of this triangle over here, and it is rotated. So we've translated it, and then we've rotated it. And so we have this. Now, something interesting about this angle that we know. This angle and this angle are corresponding congruent, and this angle are corresponding congruent. These two angles have to add up to 90 degrees because according to the triangle angles sum theorem, all three of these angles interior to the triangle add up to 180 degrees. So since these two add up to 90 degrees, that means this and this add up to 90 degrees, and we know that in a straight line there's also 180 degrees. So this angle right here is also a right angle. So we have this triangle and this triangle. They're copies of each other. One is just a transformation of the other because it's been translated and rotated, and we've created another right triangle. Now we're also going to connect this vertex and this vertex by a line. You are allowed to construct lines in plane geometry because through any 2 points is a line. That's one of our axioms. So we have this, and now what we've created is a trapezoid. This side is parallel to this side, and we have a quadrilateral here. So we have a quadrilateral with two parallel sides, so we've created a trapezoid. We know that from the theorem that the area of the trapezoid is going to be 1/2 the base, and we're going to use the parallel sides as our base 1 and base 2. So we have A plus B, and then the height is going to be this side, so it's A plus B. And we also know that the trapezoid is made up of 3 triangles, and so the area of the trapezoid is the sum of the area of the 3 triangles. So area of a triangle is 1/2 base times height. We know that the sum of these 2 triangles should make a full rectangle, but we're just going to go through left to right and look at this. Base times height is A times B, so we have 1/2 AB plus, this is C times C, so we have 1/2 C squared, and then the other 1/2 AB. So when we simplify like terms here, we're going to get that this is AB plus 1/2 C squared. Now, this was the area of the trapezoid looking at it as a trapezoid. This is the area of the trapezoid looking at the triangles and summing the triangles. By the transitive property, if area is equal to this and area is equal to this, then this and this are equal to each other. So we're going to set those equal to each other. And I'm just going to do a simplification here. I'm going to use a definition of exponent here to make this, since I have 2 things multiplied together, this is just going to be squared. And we have these things equal to each other. If I multiply through by 2, I can eliminate my fraction, so I'm going to do that as my next step. And so we have this nice thing here. And we're going to go ahead and expand this out. All right, and now I'm going to bring the 2AB over to the other side, and so when we subtract 2ab from both sides, we end up with a squared plus b squared equals c squared, which was what we were to demonstrate. So, this is U.S. President James Garfield's proof of the Pythagorean Theorem from 1876. Cheerful Calculations.